Okay, welcome back to a sunny day in Thailand. There's the coconut tree in the sun. So let's talk about measuring current. And you can see all of this is the GEVCU controller. The GEVCU, yes, electric vehicle controller. Power supplies, contactor, my 12 volt bus, my 60 volt bus. We have a 60 volt power supply, we have a 12 volt power supply, and we have a couple of meters. What I'm trying to do here is basically simulate the motorbike without having it up here in my room. This is representing the 60 volt battery pack. And these lights here are representing a small motor. Basically, when these are turned on, each of them is a 20 watt power consumer. I've got 5 there, so that's 100 watts. That's a pretty small motor. I have a 3,000 watt motor on the bike. So this isn't going to come anywhere near to represent the amount of power that's the bike is going to use. But short of starting a fire in my room, this is good enough to test out the software and test out the wiring that I'm attempting to do here. So one of the basic ways that you can actually measure current flow is through one of these, which is called a shunt. A shunt is basically a piece of metal, but it's a very highly machined piece of metal, which is calibrated to have a very exact measurement in resistance from one point to another. And if you probably can't see it, but there's a tiny notch that's been cut in the middle of that, and that's part of the calibration procedure. And this piece of metal has been designed, when you run 300 amps through it, you will be able to read 75 millivolts of DC voltage from this black terminal to this red terminal. So what that does is it basically gives you a ratio of a certain amount of current going through here from the big terminal to the big terminal. You can read a very small amount of DC voltage across those terminals. And this is just Ohm's law. Current flowing through resistance makes voltage. This one's rated 300 amps makes 75 millivolts. So using that with a simple formula, we can figure out, based on the amount of millivolts we're getting, how many amps are supposedly flowing through that piece of metal. So how can we test this? I don't have anything that's going to give me 300 amps worth of supply or anywhere close. But if we turn this system on and we're getting, each of these is producing 20 watts worth of heat and a little bit of light, at 60 volts, this string should produce 1.7 amps of DC flowing through here. 1.7 compared to 300 is very small. So the maximum range of 75 millivolts from here to here, we're only going to be getting about 0.4 millivolts across here. And that's tiny. That is an incredibly tiny reading. So what I've done is I've got a couple of my meters here. This one's going to be measuring the amps flowing through the main part of the circuit through the battery simulation, and that should read 1.7 when everything powers up. Let me position the camera a little better. And this meter is set to read the millivolts across the shunt, so that's why it's in millivolts range, and this is in amps range. So if we turn on the 60 volt switch, that simulates that the battery is now connected. We power up the GEVCU. You'll hear a click as soon as I hit the switch. You count 1, 2, 3 seconds, and then the lights will come on. And the 3-second delay is the pre-charge circuit. I'm running power through this 1000 ohm resistor to basically allow the capacitors in the motor controller to gently charge up before I blast the thing with full power. And this is a common procedure with electric vehicles. and it's basically why I smoked the components on the GEVCU before. So I think what we're going to see is 60 milliamps as the pre-charge circuit is on, which is 60 volts divided by 1,000 is 60 milliamps, 60 thousandths of an amp. 1, 2, 3, lights come on, 1.7 amps, and this is going to read 0.4 millivolts. So let's just give that a try. Pre-charge, 1, 2, 3, 60 millivolts. One powers on, 1.7 amps, and 0.4 millivolts. So we are actually correctly simulating the motorbike with a tiny amount of current flowing through the shunt right now. But all the math works, and the next step is going to be to hook up the shunt to the GEVCU, which I'm a little gun shy about because I blew up the GEVCU before the first time I tried to do it, but I guess I'm going to have to give it a try. So keep your fingers crossed. Okay, kids, this is the moment of truth. I'm back to where I was last fall, but a little wiser for all the pain. Everything is hooked up. I actually tested the circuit at the connector. I'm getting 0.4 millivolts at the wires coming into the GEVCU, so all the signals are good right up to here. What we're worried about is this diode pack, which I blew up last time, and this A to D chip, which I blew up last time. I ordered them from China. Both have been replaced by my helpful cell phone repair guys at the local mall. So watch here and here for smoke, and I'm going to keep looking at the meters over in this corner. Battery pack on, 12 volts on, pre-charge, 1, 2, 3. I don't see any smoke. Oh, no smoke. Oh, baby. So, let's see what we can read from the software, because that's all that really matters. We all want it to come out nicely into the software. Okay, the GEVCU is powered up. Let me plug it into the laptop. We'll bring up the serial console and see what's happening. Okay, we are talking to the serial console. Now, before we can actually read current, we have to calibrate it. And there are 3 things involved in that. There is the offset and the gain of the analog to digital converter that is part of the GEVCU system. And you can do that by hand, but by reading the source code, I found out there's a little bit easier way to do it using this pack current calibration command. But what I did to short circuit this a bit is the offset I'm going to set to 0 by hand, because that's meant to be what the GEVCU is seeing when there's no current flowing through. So I'm just going to leave that as 0, and I'm going to run the packcal command. Pack C cal equals 170, because we've got 1.7 amps running through the shunt right now, and it wants the reading in 1/100th of an amp. So you take 1.7, multiply it by 100, we get 170. Because the source code likes to use fixed point math rather than floating point math, because these Arduinos and the embedded computers aren't really good at floating point. So all the calculations happen and everything's multiplied by 1,000 internally, or sorry, 100 in this case. So let's set that to 170 and see what happens. Okay, so the software performed 500 reads of the analog to digital output, added them all up, divided by 500, and then calculates the gain for that circuit at 52. It seems very small to me. 1-to-1 gain is supposed to be 1024 according to the software, and you can actually see that in play up here for the other analog to digital inputs. It may be that our 1.7 amps running through the system isn't enough to give a valid reading. I'd really like to be putting 100 amps through this for a more valid reading, but that's all we've got today. Let's run the show me the raw value command, which is L, and this will read all of the raw values coming into the system. You can see the battery is reading 59.38, 0.44, 0.06 volts, which is pretty close to what I would expect, but the current is always coming back as 0. And that's not good, because I can't tell if it's because there's still something on the circuit board that's bad. There's potentially a calibration issue because I'm not giving it enough amps to successfully perform a calibration, or something. But and then the other factor is, Jack has said in the past, oh, the current reading on the GEVCU is all messed up. Even though there's some very expensive chips and a lot of thought went into the circuit, he says it just doesn't perform reliably. So the only thing I can do is use another kind of device to read current out of my battery pack. That's going to be either a shunt or a Hall effect sensor, which hopefully will give me values over CAN bus, and I can just read them that way as another CAN bus device on the CAN bus. So that's what I plan to do. Now I got to go search the world for CANbus-based DC current sensors that is going to read up to about 100 amps. Okay, here we have a 1000 ohm resistor, which is the same as I have set up in the pre-charge relay. It's going to do the job, but it's not getting us into the realms of current where we need to be to calibrate the shunt. So let's fire it up and see what happens. So that's pretty much what we expect. 60 volts divided by 1000 ohms is 0.06 of an amp, 60 milliamps. And that's not going to help us because the current shunt is rated for 300 amps and it only puts out 75 millivolts at that current range. So I need something with a lot of current and a lot of dissipative power capability, and this resistor isn't going to do it. I need something like this, which of course I don't have in my town, so I got to go to China for it, and I'm wondering whether it's just feasible to do that or not. The next test, we're doing a 4.7 ohm resistor, but I measured it's actually 5.8, so the plus or minus 5% is a little bit out of tolerance, but when you're talking that small, that's not a big deal. So 5.8 ohms into 60 volts gives us a teeny bit over 10 amps, so I'm hoping my 10 amp DC amp meter will survive this test. I don't know if the resistor itself will, because it's the only thing in the circuit right now. 10 watt resistor is probably going to go up in smoke, so let's see what happens. And oh, poof, let out the magic smoke. It all happened so fast that and smoke is continuing to pour off it at about an amp, right about an amp. But I think we lost the majority of the resistance in that. I can see it glowing orange from inside the ceramic. So you can see the kind of power we're hitting here, and what that tells me is I don't have enough low resistance, high wattage components to be able to sufficiently test and calibrate the shunt. So we have to go to plan B. As you stare out on my beach, I would ask you to subscribe to my channel and click like on this video so YouTube thinks I'm worthy again, and I have so many people on my channel that they'll give me 10 cents a day in ad revenue. So I thank you for that.